Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. Thank you all for coming. It's my pleasure to introduce our speaker today, Professor Matthias Treuer. He comes to MSR all the way from Zurich, where he is a professor of computational physics at the Institute for Theoretical Physics. He's also been a many-time visitor at Project Q down in Station Q in Santa Barbara. He's a pioneer of cluster computing in Europe, having been responsible for the installation of the first Beowulf cluster in Europe with more than 500 CPUs in 1999, and the most energy-efficient general-purpose computer on the top 500 list in 2008. He's a fellow of the American Physical Society, and his activities range from quantum simulations and topological quantum computing to novel simulation algorithms, high-performance computing, and computational provenance. He is the author of the Boost MPI C++ library for message passing on parallel computers, and the leader of the open-source ALPS library for the simulation of quantum many-body systems. So without further ado, please join me in welcoming Professor Treuer.
Okay, thank you. And what I was told often is that there are two words that scare computer scientists, and it's physics and quantum. So I'm glad that so many may come here, and I keep it at a simple level where it should be no problem to follow. And if there are people here who have some physics background, then in case you have questions, ask me, and I'll show the details later. What the starting point is that we see that Moore's law still holds. The speed of the fastest machine still increases exponentially, and soon we should reach an exaflop. But the question is, how long can that continue? And essentially, the consensus is that in the next 10 years or so, it should slow down or stop. The main physical problem is that when you look at the CMOS device, the insulating layer now approaches about the nanometer, so it is 4 atomic layers thick. When you make it thin and scale it down further, then it will no longer be insulating. So there are the challenges, and one reaches the limit of scaling, quantum mechanics becomes important. But the main problem that we face right now already is that as we stop scaling, we need more power to run the machines. Because as we scaled it down, the power, the density stayed constant. Now to get more the performance, we need bigger machines and need more power. So to get to a petaflop and then you have the exaflop, in the past years, we needed always about 100 times more cores to reach 1,000 times more power. So in the 90s, I used the YMP, and they sounded a great machine, 8 CPUs and the gigaflop. Then later, we used machines with thousands of cores, and now my friends in Japan, they use hundreds of thousands of cores, and that causes problem. One problem is Amdahl's law. It gets just impossible to write good codes on those machines. It gets hard to scale. There's a problem. The code that we write scale to about 10,000 cores, and beyond that, we can do simulations, but they are not the real problems we want to solve. So I'm not going for the petascale. I rather want to solve a real problem and not get a record. But the other problem that we already face is power. The power that our clusters use gets more and more. And what limits our clusters at the moment at the ETH is the amount of money the vice president wants to give us to run the machine for the power. So I think that will be the limiting factor. So one can now scale things up, improve things slowly. But at some point in time, there will be an end, and at that point, we need to change the way we do things. And Rajib Yahasra from the Intel thinks that beyond 2025, we'll need some miracles. So what we can instead do is we can now already think about a disruptive change and think how can we make use of quantum mechanics in solving some special problems in computing, while Moore's law still works for a while. Now, quantum mechanics is carried to many. It's what draws some to the physics. It's what keeps others from physics, like we heard before the talk. But it's already more than a century old. And the last century was a century of physics, and there were many innovations due to physics, but almost all of it is classical. There are very few quantum devices, and here I have a quantum device that you can buy. Pass it around. It works on Windows, macOS, and Linux. So we have some quantum devices that work like they are quantum random numbers, quantum simulators, and in May of this year, the first quantum computer was solved, or they call it the quantum computing systems. I will not talk about that because I will talk about things that work. I can mention something about D-Wave 1 if somebody asks later, but I want to leave that for now. And I think my hope is more for the future Windows Q quantum computer that we might have sometime. But now first to the machines that actually work and why it's important to actually make sure they work and what they do. I want to start with something simple, namely a quantum random number generator. And the question is, where do we need random numbers? And where do we need good random numbers? So why should one have a quantum random number generator? The main commercial application for quantum random numbers are the online gambling and lotteries, because there you really want to be sure it's random. The lotteries really have to prove that they are unbiased and fair and so on. And for the online gambling, you don't want a hacker to make use of some of the flaws in your generator. Well, what I use for simulations for quantum systems in statistical physics, then it's also widely used in the finance to sample the possible futures of the stock market. And how do we usually get random numbers? We get random numbers using an algorithm on a deterministic machine. And of course, that's not random because it always gives the same results if you start with the same input. So it's called a pseudo-random number. And that's something that just looks random, that looks unpredictable, and one wants to use some fast, simple algorithms. Now, the first problem is that these numbers are not random at all. They're completely deterministic. There's no entropy, and if you know the algorithm, you can predict the next number. But it might be good enough, and so one does many tests. Do they look random? Are there correlations? And those that pass the tests, they are termed to be good random number generators. And then a problem comes up every 2 years that you do a simulation and you calculate something with high accuracy and you find the result that's off by 40 error bars. That's just completely wrong. That was seen the first time back in the year 1992, and it comes up often now. Yeah?
It famously came up in 1963 or 64.
Already,
about
yeah.
a pseudo-random generator that IBM then used for a generation.
Yeah.
The infamous Randu. Look at that.
Yeah.
You will shudder.
So it's a well-known problem, and it comes up every time. One uses better ones and better ones, and one tests them, and one uses them, and then a student spends weeks finding a bug in their code because the test result is wrong until the professor says, maybe it's a problem of the random number generator. And then they say, hey, yes. And then one uses a better one. And then somebody runs in and tells me there's a bug in my code. And I ask him, have you changed the random number generator? And he said, why? They should be good. So the only test that you have is your own application. If that gives the right result, that is good enough. If it doesn't give the right result, then it's not good enough. So we essentially have to run everything twice. There are generators that are better. The cryptographically secure one, we tried using them. There, at least, if you find a problem, you have solved a hard computational problem. The problem is they are about a factor of 1,000 to 10,000 slower, and they are too slow. They give too few numbers. So the idea is you can get a quantum random number generator and produce random numbers based on quantum mechanics. How does that work? It costs about 1,000 euros, so $1,500. And what is in here? In here there's a photon source that emits a photon. And the photon slides out, and it hits a semi-transparent mirror. And here now, there's what you have to know about quantum mechanics. And a friend of mine, Shankar at Yale, he explains quantum mechanics using quotes from Yogi Berra. There's a famous quote, "When you come to a fork in the road, take it." That's what really happens. So the photon takes the fork, and it follows both paths. So it came here, then it follows both paths. And then we look where the photon is. Is it here or is it there? And when you look where something is, then it's always only in one location. So by observing it, by measuring it, and there's another Yogi Berra quote for that I don't remember, then it shows up in only one location. When you really pinpoint it, when you want to localize it somewhere, then it's only in one location. And which one is chosen purely at random? There's a physical mechanism here that produces randomness. And then I record a random bit, 0 or 1, whether it's left or right. Now, does it work? Of course, let us assume that quantum mechanics is correct, and there's good reason to believe it. So does this device work? And what you can do is you can look up, and there's a certificate by the Swiss Office of Metrology that certifies that the tested device has passed the die-hard tests, and it's random. So it's certified. And then when we saw our results later and they asked them, they said, of course, any certificate only means as far as the test can tell.
How do you know the mirror is really exactly half silver, and that doesn't introduce a bias?
That's the first problem, bias.
Wow.
Yeah, good point. It's not perfectly, but sometimes it gives you more ones than zeros or more zeros than ones. What you can do, there is a version of this which in the driver software does von Neumann the biasing. You take 2 bits. If the 2 bits are the same, you discard it. The 0, 1 you map to a 0, the 1, 0 you map to a 1. That way the bias is gone. And your bit rate is reduced to a quarter. So instead of 4 megabit a second, you get only 1 megabit a second from the device, but without any bias. 1 megabit a second is not fast because we typically need about a gigabit a second. But there's another problem. When you look at correlations, there shouldn't be any because quantum mechanics, and that should be perfectly random. So we measure the correlations, and when you measure for a few days, then you find there is an autocorrelation of about 3 times 10 to the minus 5. It's tiny, but it's worse than a cryptographically secure pseudorandom number generator. It is not random. Now, the problem here is not that quantum mechanics is incorrect. The problem is that the detector has a memory. If the detector sees a photon, and the next time you ask where's a photon, then the detector can sometimes trigger again because of the previous photon. There's the photon punching, sometimes there can be 2 photons, and then there's a tiny bias that the same detector triggers again. One can solve that by just increasing the time. This is, so if you go to about 4 or 5 times the distance, then it's safe, and if you reduce then the bit rate by another factor of 10, then you should be safe. But now we've reduced the bit rate by a factor of 40, and we're still not completely sure that it works. So what we can instead do is I then talk to a person in quantum information theory, Renato Renner, and he told me, but hey, don't you use randomness extractors? Then I asked him, what is that? And then he told me, but that has been invented by theoretical computer scientists just to produce random numbers. And that was then the key to making this thing work. What we do is we view the bit stream not as a random stream, but as an entropy source. And we look at those bits, and we extract, for example, 2,048 bits of it. And then we look what is the entropy density in that. And we estimate that and find it's about 0.99. So there's only a tiny, tiny loss of entropy due to the bias and the correlations. And then what one can do is one can use a two-universal the hash function. One takes a random bit matrix that one fixes once and for all. And one does the multiplication of the input vector with that the bit matrix. And from 2,048 bits of entropy that we feed in, we can extract 1,792 bits of random numbers. And if this matrix M is chosen with true random numbers, then the probability to find any non-randomness in the output is less than 2 to the minus the entropy the density times the number of your bits minus the ones we extracted divided by 2. And that here gives us that the probability to find any non-randomness is less than 10 to the minus 35. If you want it even better, you just extract fewer bits from it. So that way one can then actually prove that the probability that it's non-random is bounded by that number, and one makes it work, and the only change that we need is a change in the driver. Yeah.
Less expensive forms of entropy you can use?
The other question then, are there less expensive forms of entropy? That's what one has to explore. There are forms of entropy that one could use, for example, thermal noise in a resistor. That's what we're looking at. The problem with thermal noise is you cannot prove on physical grounds what the entropy is. In the quantum device, you know the physical mechanism, you can actually prove it. With the thermal noise, you can estimate it. So this is the stronger thing. But yes, we want to find faster and less expensive sources, because that's pretty expensive for low bit rate.
The proof that you have there seems like it's not only dependent on your controllable error probability,
yeah,
but also on the assumptions that you're making about the correlation. And
it depends on the assumption. Yes, it depends on it depends on how good my min entropy estimate is, and what assumptions go into that.
Yeah.
Yes, and so how did we get that number? What we did is we assumed that the correlations decay exponentially, or decay fast enough. And the only thing for that estimate that I need to assume is essentially that the correlation long times are bounded by the values at the shortest distance that I measure. That went into that estimate. It just should not increase beyond that level anymore in the future. And that's the physical thing we know about this device. Of course, there could be something hidden in the quantum in physics beyond quantum mechanics, or there could be long-term correlations, but that's very unlikely. Yeah.
I leave Monte Carlo to you, but if I have random numbers, it's only that problems are perfectly good for crypto, because the bad guys don't have an interesting advantage in guessing about the key.
Yeah.
The keys are biased, but I don't care.
Okay, what question? Yeah.
I guess I'm still a little unsatisfied because of that assumption, because that assumption doesn't seem to be any weaker assumption than the typical cryptographic assumptions that could be made about a good one-way hash function or a good pseudorandom number generator.
The assumption that goes in here is the quantum mechanics is valid, and that
it's the entropy estimate. That's
the entropy is estimated based on the assumption that the correlations do not increase anymore after a millisecond.
Right. Is that
In
very
these
different from
devices,
assuming a certain pseudorandom number generator is secure?
I think that is more secure because in this device I can measure the correlation time, and the correlations decay with an autocorrelation time of about 100 nanoseconds. And then memory should be lost over time in those devices and the time scale. So if you see that after a second things go up again, that would be worth a Nobel Prize. Yeah. Okay. So now let me go to a device that costs even 1,000 times more. If you think that was expensive, now we go to something that costs 2 to 3 million. And what we want to do is we want to simulate quantum systems. And first, let me show you why simulating quantum systems is hard, why we need it, and then what we can do about it. The basic problem is, here's the theory of everything relevant in daily life, the Schrödinger equation with Coulomb forces. Essentially, physics knows the theory of everything unless you go to extreme conditions. This equation here, the Schrödinger equation, explains most of physics, all of chemistry, biology, the stock market, life, and more. It's a simple linear partial differential equation. The only problem is it lives in 3 n dimensions, and n is of the order of 10 to the 20. So we just have to solve a linear PDE in a huge number of dimensions, and the complexity of solving that grows exponentially with the number of dimensions. If you have the m points in 1 dimension, then you need so you have m to the 3n points in n dimensions. So that's the basic problem. It's a simple problem, but it just scales horribly. So we have to reduce it to something that doesn't scale as badly. And since I mentioned Nobel Prize before, here's the first Nobel Prize to Kohn and Popel. What Kohn has proven, and it's a one-line proof, so you can get a Nobel Prize for a one-line statement. That is that you can find the ground state of a quantum system, not by finding this huge wave function, but the only thing you have to do is you have to minimize a functional of the density. The density lives in 3 dimensions, so you have to solve a 3-dimensional minimization problem. You have to find the density distribution that minimizes this functional. The only problem is we don't know that last term here exactly. That one-line proof that it exists doesn't tell you how to compute it easily. It was recently shown by Verstraete that is hard even on a quantum computer. It is QMA hard to find the true functional. So what people do, they approximate and find something that's good enough. Yeah.
What does the SC stand for in ESC? X. Self-consistent?
XC, that's the exchange and correlation term. You have one term that is the external potential gravity, the nuclei, and so on. You have the kinetic energy of the electrons. You have the classical part of the Coulomb energy, and then you have the rest. That's tiny but important. But if you apply that, for example, to the silicon, then you find the band gap here, and that band gap to excitation is what makes the semiconductors work. Now, to solve this equation, you need big machines. And to demonstrate that, I'm showing here the fastest machines that run on Jaguar in Oak Ridge. And essentially, all the codes in the world that exist that run at faster than a petaflop solve this material science problem. This needs huge machines, and essentially no other code yet reaches the petaflop. So these are big problems to solve this still. And now the question is, can you find the interesting things with it? And one interesting question is, can we, for example, find a good superconductor? The superconductor is the material that has no electrical resistivity. And it was back in 1911 in Holland. And as you lower the temperature, in the mercury, the resistivity drops, and the wire carries the current without resistance. Then it took nearly 50 years to explain it. And of course, one wants to increase the temperature at which that happened, because the first one here was at about 4 Kelvin, which is very, very cold. Here's now the highest temperature at which material can be superconducting as a function of time. And it grew slowly and slowly, and then is saturated at about 30 Kelvin. Until in 1986, Bednorz and Müller found the so-called the high temperature the superconductors. And just suddenly it jumped up rapidly in a few years to 140 Kelvin and is now stuck there. The big question is, why are those materials the superconducting? And the more important question, if that was increased already by a factor of 3 to 4, can we increase it by another factor of 2 and reach room temperature? And then we'd have the power lines without loss. It would be really great, levitating trains and all. So that would be really useful. And there was a big hype in those years about that will be happening soon. But since then, we are stuck at this temperature. And the question is, can we simulate it? So what we can do is we can use the density functional theory that worked so well for silicon and try to apply it to those materials. And the problem is, and I don't want to go into detail, it just gives the wrong results. When you have this material undoped in the experiment, it's an insulator. When you simulate it, it comes out as a metal. It's qualitatively wrong, and just because here in those materials, this exchange correlation term, which you don't know, is so important. So what's the answer? We need to solve the full quantum problem. We want to solve a simplified toy model, at least for those materials, but we need to solve this big problem. And now I want to show you how we can solve exponentially big problems and what is the problem in quantum mechanics. What we can solve, or what we can use to solve high-dimensional PDEs is the Monte Carlo method that was invented in the 40s by Ulam. I don't know if you know the story, but he was sick and in bed and he was playing solitaire. And he asked a problem that was also exponentially hard, namely, what is the probability to win in solitaire? And if you have 52 cards, there are 52 factorial possible games. And if you want to solve it exactly, you either have to be very, very smart and find then exactly a solution. But he instead had another smart idea. He played it 100 times because he had time. And okay, he didn't have Windows yet, but it took longer. But then he played it 100 times and won 15 times. And so he knew that while he didn't know the exact answer, it was somewhere around 15%. And that was good enough for him. So if we just want an estimate that we can get as precise as possible, then we can do that by sampling a small subset of the exponentially large number of states. And the general algorithm for that was then invented in 1953, so quite a while ago, by Metropolis, Rosenbluth, Teller, and Teller. And that's the Metropolis algorithm. Now, many people have heard about the method, but very few have ever looked at the paper. Has anyone here seen the paper? The paper is interesting because, first of all, there are 2 husband and wife teams on the paper, and the person actually inventing the algorithm was a woman, Rosenbluth. Metropolis was just alphabetically first, and he was the one who built the machine. That machine was also special because it was the first machine that ran at a kiloflop. It was a big challenge at the time what to do with such a fast machine, and that's why Teller invented that method, and that's what we use now when we don't know what a big machine is useful for. The Metropolis algorithm will always work. And it's always important to find a good motivation for a paper and find a good first sentence, and this paper beats them all. The purpose of this paper is to describe a general method of calculating the properties of any substance. Wow. Yeah?
I presume any substance means plutonium.
Including plutonium, yes. Which is still a challenge. And there's another sentence down here. The second one said classical statistics is assumed, and that's the problem for plutonium. But it's a simple method, and I will just show it because that will then point to the problems with quantum systems. What you do is you start with any configuration of your system, of your atoms, whatever. You make a small change, like you move one particle around. You calculate the ratios of the weights of the new to the old configuration, and you accept the new configuration with a probability that is the minimum of 1 in that ratio. Very simple, but a great idea, and in principle, it works for anything. But it's slow. And let me show you why.
What are those weights again? Calculate weights.
Those weights might be the weights of a state, which is exponential of minus the energy divided by the temperature in the classical system. So it's just the ability to be there at the temperature you had. If you want to find the ground state, then essentially what it means, you accept it always if the energy goes down. When it goes up, you don't accept it. Now, let me try to show you how it works. And here I have a simple model of a magnet. Let me try to run that. And that's a magnet that can point up or down. Up is white and down is black, and I'm at low temperatures, and so it's just stuck. The simulation is actually running. I can increase my temperature, and it starts to fluctuate. Can increase the temperature more. Now it's so hot that the magnet is no longer magnetic. It's half black and half white. Half up, half down, so it's no longer magnetic. Now we can cool it down again to close to the critical point where the magnetism vanishes. And now we see that some big domains here start forming, black and white ones, and it starts to order, but still half black, half white. But you also see that now nothing much changes anymore, and that's what I want to show. That those local spin flips that do, changing squares from black to white, that does not change much in the global structure. This is called the critical slowing down problem. It gets even worse if we lower the temperature. Let me now go again to very low temperatures, 0.1. It should turn white or black, and we can now wait a long time. So in principle, it should work, but it can take forever. And so we need to be smart and invent faster methods. So in principle, it works, but we can do huge progress using faster methods. Like, let me go back again to close to this critical point, and there are those cluster update schemes by the Svensson and Wang, which is the smart way to find the graph to flip. And that code is about 5 lines longer, so it's 20 lines instead of 15 lines, and it performs a factor of here about 40,000 faster. So and that's a key, that it's important to find better algorithms. And to demonstrate that, one of my colleagues here looked at how he simulated that model over the years, and he started back in '72, and he plotted how much did the raw computer speed of his machines increase. That was this line, which essentially followed the Moore's law, and how much faster did this code become with the combined improvements of algorithms and hardware. And that was also an additional exponential growth, and in principle, if you run the modern algorithm on a 30-year-old machine, if you still had it, it would run faster than using the old method on today's machine. So there have been speed-ups of the factor of 10 to the 5, 10 to the 6, and more, just due to methods. And I think one good point of the end of Moore's law will be that we'll focus more on methods instead of hardware. But we can now often simulate hundreds of thousands of quantum particles. The progress came through the new ideas, the new methods, thoughts that work a factor 10 to the 5 faster. We have another new method for the plutonium that makes that a factor of 10 to the 6 faster, but that's used now not by us, but in Livermore, because I'm not that interested in the plutonium. We scale our codes well to about 10,000 cores. There are a few colleagues who scale it further and get the Gordon Bell Prize by scaling it to 100,000 cores on artificial problems. I prefer to stick with the real problems and stop at 10,000 cores. For some codes, we use now the accelerator chips, like the GPUs or the successor chips in the future. And that helps a lot, and that allows us to solve the bigger problems. What we need to get those codes to run is libraries that help us simplify the coding, because we essentially have to help a physics student write a sensible code that scales well. So we use some the libraries for that. We use the workflow systems that are provenance enabled. And the goal that we've reached now in two papers already is that that just by looking at the paper and clicking on the figure, you can reproduce and rerun the whole calculation. And the next step, which we work on now, is the new machines which we'll get will not survive the runtime of the code, so we want to make the codes the fault tolerant, and that works pretty well for those simulations.
What is provenance enabled?
You want to have a workflow system that helps you record what you've done. So when you have your result, your graph at the end, with that you have all the metadata that tells you where it came from, how it was calculated. If you just take your numbers and you copy them into Excel and make a plot and copy that into your paper, and then you ask, okay, hey, which version of the code did you run that on, or on which machine? Then the students say, I don't know, that might be the buggy version, let me redo the whole calculation. You want to look at the final data and trace the lineage back where it came from. So with that, we can, for some type of quantum systems, we solved up to tens and hundreds of millions of quantum systems. But the most interesting are those materials. In the material, there are electrons, and the electrons are a type of particle that the physicist calls a fermion. Those who know quantum physics know about the Pauli principle. For the others, I want to note just that the effect is that you can simulate those electrons, but the weights you get can become negative. That goes back to the question of the weights. You sample the states, and some come in with a positive weight and some with a negative weight. So you get a huge cancellation problem. When you want to sample it and you have a negative weight, then I want to accept a state with a probability of -1/2. Now, I don't know how to do that. So you then try to find a way around that, and we could prove that solving this sign problem in general is an NP-hard problem. So we might find some cases where it works, but in general it will not. And now we come back to the quantum hardware, because Feynman was one of the first to discover that problem, and he said, to solve a quantum problem, you need to use quantum mechanics. So we need to use a computer that is based on quantum mechanics to solve it. And for those models, we don't aim for a full-fledged quantum computer yet. We aim for a quantum simulator, which is essentially a special purpose device to solve a model. And last year, science has chosen the quantum simulators as one of the breakthroughs of the year. They had a total of 10 scientific topics for the breakthroughs. The winner was a quantum machine. The 8 other problems were all in life science, cancer research, protein folding, and so on. And one more was physics, namely the quantum simulators, that they passed the first key test, and that's what I'll tell you about now. So what are the types of machines that we can have to compute? The first ones were analog, like the mechanism that was found in Greek. It's about 2,000 years old. It was the first machine to calculate where the planets are. Nowadays, we have programmable digital machine. Now, what a quantum simulator is essentially a quantum analog of this Terra machine, an analog quantum device. In the future, then, and that will not take another 2,000 years, but will be fast, it will be the quantum computer. And I want to focus now on how we can use the classical machine to validate a quantum simulator. And that goes back to the DARPA program on the optical lattice emulators. They said, okay, that since people can build such a quantum simulator, they give us money to build it. But in the first 2 years, we have to build one for a model that we can solve, and we have to show that this quantum machine gives the right answers for a problem that we can solve. And then we got some more money to solve some problems and build some that we can't solve from this classical machine. But of course, there's a challenge to me, and I try to make my codes faster and faster to solve the same problem still. So, but what are those machines built on? It goes back to work by Steve Chu and others, who's now the Secretary of the Energy here. And he found a way to cool and trap atoms with the laser light. That was the Nobel Prize in 1997. And then about 4 years later, there was a new Nobel Prize for the achievement of a Bose-Einstein condensate. I will now mention quickly what that is and why it's relevant to quantum simulators. Essentially, there are 2 types of quantum particles that have been found so far in nature. There are bosons and fermions. There's a third type, the anyons, that you have the station Q looks for the quantum computer, but they have not been found so far. So we take a gas of atoms down at very, very low temperatures. We go down to the nano-Kelvin temperatures and trap 1 million of those atoms. And now, depending on whether the total number of neutrons, protons, and electrons is even or odd, it's a boson or a fermion. For example, lithium-7 is a boson, and those bosonic particles, when you cool them down to 0 temperature, they all want to go into the same state. The fermionic particles, when you have the odd number of the fermions, like the electron also, they want to have just 1 particle per state. That's for example what explains the shell structure of the atom. You have just 1 electron per state. Now, bosons are computationally easy. In fermions, we get the same problem, and they are computationally hard. So, a model with bosons, we can simulate. One with fermions is then what you want to solve. So, you can now build an atomic quantum gas simulator. It costs about $2 million. It costs about 2 to 3 years to build for a team if you know exactly what you do. The challenges are you have these gases at nano-Kelvin temperatures. You need to control the noise down to nano-Kelvin. You need to really line up your lasers and all perfectly. And you need to be able to take the pictures of the atoms, so it's a big challenge to actually build it. But then once you build it, what can you do? So I need to show that here in this glass chamber there's the quantum gas. And then what they do to find the state is they take the gas and they drop it down. They drop this cloud of gas and it expands. And then they just take a picture. And that picture now shows that gas cloud. And what it does is it shows the velocity distribution in the cloud. Those atoms which were at rest just drop down. Those who were flying out, they fly farther. So once you take the picture, you see the momentum distribution of your cloud. And that's where this Bose-Einstein condensate comes in. If you have bosons at very low temperatures, they all occupy the same state. So they all are at rest in the center of the trap. When you now drop them down, they shouldn't fly apart because they're all in this state at rest. And here are three pictures as they cool down the gas. A sharp peak formed in the center at velocity 0. And they found the Bose-Einstein condensate, and they got a Nobel Prize. Now can we do more? Okay, that's a simple gas, but now we want to simulate a more complicated model, like for electrons in a the material. For that, we need to add the crystal lattice. Now we can do that by just adding an optical lattice by adding 6 more lasers and 6 more beams and all. And then you take those 6 laser beams to form a standing wave pattern of light. And then you have those atoms hopping around on a lattice. Now you build a quantum lattice model. And all you have to do now is you have to build the model that describes your the material and measure its properties. Does it work? We wanted to validate it. So we can simulate the same number of your atoms, about half a million atoms, if they are bosons, on a big lattice, and a single point takes about 8 hours on a single core. So it's cheap. But then we had to model all the details, the same lattice structure, the same number of particles, the same temperature, and we measured the same quantities. And then if this quantum device works, then our simulation should better give the same results as they measure. If not, then the quantum device doesn't work. So we compared, and of course it didn't agree. Why did it not agree? As I said, because we have to model all the details of the experiment. Then we learned that it drops down only a finite time, so there's still corrections to what you actually see. It's not the limiting value, which is the velocity distributions. Then we have these lasers, and there's some noise in the lasers. That nasal noise heats the gas, so the temperature changes. Then we have a lens through which we take the picture. The lens broadens the signal that we see. We have the camera with the pixel size. And once all of that was taken into account, then we looked again. Do things agree? And this is what we got at the end. This is the simulation. This is the experiment. And here's low temperature, and they're high, and essentially it agrees, except that the simulation is still clean and has the smaller errors. When we look more closely, then it's just wonder their full agreement here. So it works. That's the good news. So we can actually build a device that implements a quantum model. And when we simulate it, yes, the device really gives what you want. So we actually built a quantum model in a quantum device. Now, the next step. The next step is we want to solve a hard problem. For example, we want to solve a high temperature superconductor. What do we have to do for that? If you want to do that on a classical computer, it becomes an exponentially hard problem. If you want to do that on the quantum simulator, we just have to change the isotope. Like we just have to change from lithium-7 to lithium-8. The rest of the machine can essentially stay the same. Of course, there are engineering problems, but that can be done. And it's not much harder for them to do fermions than bosons, while for us on the classical machine, it's much harder to do the fermions. What's the status there? To validate it, it's much, much harder. It's about for the small systems at high temperatures they're at now, it's about a factor of 1,000 harder, but we could validate the first results. And we now wait for the first things that we didn't know, and those numbers should come soon from them. If we want to simulate a real material, like you mentioned, the plutonium, there's no way we will ever model the lattice structure of that in such a system. So for that, we will later need the quantum computer. But simple models one can actually build and then measure. So one can build a special purpose quantum device to solve hard quantum problems. So to summarize, we have the first quantum devices, and they seem to work. Like the quantum random numbers work. They're a bit slow and cost a lot, but it works. The quantum simulators cost much, much more, but that's the next stage. And slowly they will reach models and the temperature regimes that will not be solved on the fastest machines. So they will become useful. Quantum computers will be the next step. But in my point of view, you shouldn't sell a quantum computer before you validate it that it works. So that will be the next thing to do then. That was funded by DARPA, as I mentioned, and the Swiss Center on Quantum Systems and Technology, where we work on quantum dots, simulations, qubits, and more. And the people who did the work for the quantum random numbers, it was a student, Raphael Gasolka in Zurich. The simulations were done mostly by Claude Pollet at the ETH, and the experiments were done in Munich by Stefan Trotsky, a student there. Thank you.
For quantum computers, you can't measure them, so what difference does it matter whether they're random or not?
What?
I thought that quantum computers couldn't measure the output out without inducing some error somewhere else.
So for a quantum computer, so in a quantum system, when you measure something, you will change the state of the system. Is that what you mean?
Yeah.
And that's exactly what those quantum random numbers are based on. Because if you say the photon is in two places, and you measure it somewhere, then you change the system, then it's in one place only. But which one is chosen randomly? And that's the process that underlies the device. So that when you measure it, you have some random selection, and that's what we use. For a quantum computer, you wanted to compute a single answer that you can measure just, and it's just in one state at the end. Yeah.
if I remember right, AES in counter mode runs about 2 cycles per bit and is secure enough for NIST and NSA. Is that really too slow? If you run the standard block cipher in counter mode,
yes,
you get stuff that whose only distinction from pseudorandom is that there's no birthday paradox. Is that really too slow?
2 cycles per bit, that would be slow compared to some of the ones we use, but it would approach the range where we
computer cycles, not per second.
Yes, so where it can be useful for some methods. The ones we tested and we tried, they need about the 10,000 cycles per bit. Yeah. So, but with any of those generators, the basic thing is there's no underlying guarantee that there's entropy in your stream. But in principle, it is always deterministic, so there can always be problems. And yes, there is the potential that we don't know the physics yet that makes this device have some strange relations of the long times, but that's less likely than there being a problem in one of the pseudo-random number generators. So it's at the different level because this device does have some true entropy in it, which the other methods don't. Yeah. Okay. Any more questions?